In principle, solving an equation with trigonometric functions that have a shift and a stretch on the inside of the function isn't any different than solving any other sort of trigonometric equation, but there are a couple points to be a little bit careful about. So let's look at a couple examples. So this is the first one. So sine of 4 theta equals minus 1/2. As usual, we can start just by using an inverse trig function to find an angle that works. So by taking inverse sine on both sides, we get 4 theta equals, and then inverse sine of minus 1/2 is, it's going to be minus pi over 6. Okay, so we need to decide when is the appropriate time to add a period and also find the symmetric solutions. So it's sort of tempting to divide by 4 right away and then find, then add 2 pi and all of that. But the right time to add 2 pi isn't after you've finished solving for theta, it's actually right now, because all of those extra solutions that you get by adding period and by finding the symmetric solution, they all sort of appear immediately when you use an inverse sine. This is sort of similar to when you take a square root on both sides of an equation. You don't finish solving for x first and then throw the plus or minus on the end. You throw that plus or minus on immediately after you take square roots on both sides of the equation. It's the same thing here. So we need to add 2 pi k right at this point, and also write down the symmetric solutions immediately at this point. So the symmetric solution is pi minus the initial solution, so negative pi over 6, and then again plus 2 pi k. All right, and now that we have all of our solutions written down, now we can finish solving for theta. So now we can divide everything by 4. So theta is minus, let's see, pi over 6 over 4 is going to be at pi over 24 plus, and then 2 pi k over 4 is pi over 2 times k. And then the same thing over here. Maybe simplify this stuff first. That's going to be 7 pi over 6. So divide everything by 4. And you get 7 pi over 24 plus pi over 2 times k. Okay, notice that this is different than what we would have gotten if we solved for theta first and then added periods and found a symmetric solution. Just for example, if we finished solving for theta first to get minus pi over 24 and then tried to add 2 pi k, well, that isn't right, because it shouldn't be 2 pi k, it actually should be pi over 2k. You can see that what happens here is this 4 has changed the period. The period for this function, sine of 4 theta, is actually pi over 2, and that's why pi over 2 shows up here instead of 2 pi. Okay, so that's how it works out if you have just a stretch on the inside of your trig function, or a multiple of the variable. Let's see what happens if you have a shift as well. So something like this. So cosine 4 pi times x minus pi over 4 equals root 2 over 2. So just like with the last example, we can find an initial value just by using an inverse trig function. So we'll use inverse cosine, and that gives us 4 pi times x minus pi over 4 equals, and then inverse cosine of root 2 over 2, that's pi over 4. And just like last time, it is immediately after you use your inverse trig function that you need to write down all of the other possible solutions. So add periods and find the symmetric solutions. So it's at this point that we need to add 2 pi k and write down the symmetric solutions. So 4 pi x minus pi over 4 equals, and then the symmetric solution for cosine is just the negative of the initial solution. So minus pi over 4 plus 2 pi k. And now we can finish solving for x. So add pi over 4 on both sides. 4 pi x equals pi over 4 plus pi over 4 is pi over 2 plus 2 pi k. And over here, add pi over 4 to both sides. 4 pi x equals, so minus pi over 4 plus pi over 4 is 0, so those cancel, and we're just left with 2 pi k. And then divide both sides by 4 pi. So we get x equals, let's see, pi over 2 over 4 pi. The pi's are going to cancel, and we get 1 over 8 plus 2 pi over 4 pi is a half, so plus a half k. And then for the symmetric solutions, we get x equals, looks like just 1/2 k. And as usual, k is any integer. So you can see this does work out just like solving any other trigonometric equation, except you have to be careful to write down all of these solutions immediately after using your inverse trig function.